Welcome all to the tutorial on hand-eye calibration. This is a very important topic since without a solid hand-eye calibration, vision-guided pick-and-place applications wouldn't be possible. Hand-eye calibration is about the coordination between eye and hand or a camera and an actor. When a vision system detects and localizes objects, it does so relative to an intrinsic coordinate system of the camera. So thanks to the result of hand-eye calibration, we will be able to transform object poses that were expressed relative to the camera coordinate system into a coordinate system that is known to the robot and that we can use to execute motion commands. Our API enables you to implement a hand-eye calibration end-to-end on any type of robot controller. And the customer can execute such a program autonomously whenever a recalibration is necessary. And such a recalibration will eventually become necessary in any type of real-life system. This tutorial provides a step-by-step guide on how to implement such a calibration program on a universal robots controller. This is the second hand-eye calibration scenario where the camera is not mounted statically inside the cell but is carried by the robot end effector. Here we can comprehend the camera as a tool, and so we're looking for the transformation between the TCP and the flange coordinate system. Calibration will require a piece of hardware, a so-called calibration pattern. I would encourage you to check out our documentation. Here we see an example for such a pattern. The robot will carry this pattern in case that the camera is static within the cell, and when the robot moves the camera, then that pattern will be put at a fixed place inside the cell. Typically, you will receive such a pattern from us, but feel free to download this PDF here and print it out yourself. But if you do so, please make sure that the printout is faithful to the dimensions set in the PDF. It's pretty straightforward to check that. You should measure the side length of the checkers, and those should amount to 25 millimeters each. Then stick the printout on a planar surface, but make sure that the pattern is as straightened out and flat as possible. Now, the calibration algorithm essentially requires as input a series of images in which I vary the relative position between camera and pattern. This applies to both cases, the static and the dynamic camera. In the former case, the robot moves the pattern, and the latter one, it moves the camera. A convenient way to start the implementation of the calibration program is by teaching those poses. We recommend a minimum number of 20 poses, but with 40 you're definitely on the safe side regardless of the application and the precision it may require. To ease the teaching of the poses, we put the camera into flash mode first. We'll do this again using the 3D Viewer app, so open up a new browser tab and navigate to the app URL on the Edge device. At the bottom, click on Configuration. Toggle the switch for image streaming, click Save, and the camera should start flashing immediately. Now, the part of the pattern that is entirely covered by the fringes of the projection, those are the parts that will be entirely visible in the image. So it's crucial that the entire pattern is visible in every image, at least the part that is bounded by the 4 outermost inner corners. Actually, teaching the pose is pretty convenient on this collaborative robot. Just drag it into the desired pose. And the projected fringes indicate whether the desired part of the pattern is inside the field of view. Independent of the service that I use on the Edge device, I need to make sure that at least one product is armed. Associated with the service are, for example, the camera parameters or any other configuration that is required to run the service. So what I'll need to do first is log into the front end and then create a product for running the calibration workflow. So let's switch to the Products tab using the menu at the bottom, then click New Product. Choose Calibration as the workflow. First, I need to pick a name for the product, so let's choose hand-eye calibration here, for example. Next, I pick the Edge device on which the calibration will be executed later. So in this case, tutorials. And finally, I specify the camera model that we're using here. In this case, it's a Ziva 2. It's pretty important that you make the right choice here, as obviously the calibration result depends heavily on the camera parameters. And of course, don't forget to click on Save and Exit. A service is armed by its product ID, and that product ID was automatically created when we just saved our data. And while I'm here, let me get a copy of that product ID so I can shortly insert it into the robot program. For that, I open the product that we've just created and then click on the yellow button next to the title. This will copy the product ID to the clipboard. Should you not be able to paste the product ID from the clipboard because, for example, you're working with a robot panel, then you can also copy it up here from the address bar. Let's switch back to the robot now, and the first thing we need to do is insert a couple of commands into the pre-start sequence. All of these commands are written in your script, and the reason for that is that the client we use for communication with the edge device is only available through your script. So first of all, we put the product ID into a variable that we can reuse multiple times in the commands below. Next, we initialize the client as we've seen in the tutorial on object detection. By default, the protocol is XML RPC, and this is the URL of the server that runs on the edge device. The next command also looks familiar. The function getProjectionMatrix just makes sure that the intrinsic parameters of the camera are recalibrated. So then we need to make sure that an execution of the calibration routine corresponds to one execution of this robot program. And we do this by using a so-called session ID. This ID is generated at random at the beginning of the calibration program and attached to each image that is acquired thereby. How to create such a session ID is entirely up to the user, but what we do here is we generate a random number between 0 and 1, then we multiply that number by 100,000 and round it down to the next integer. So we get a random number between 0 and 100,000, and finally that we cast to a variable of type string. And as I already said, this could be done in many different ways, for example, using timestamps. The only thing that matters here is that a unique session ID is generated for each program execution. Next, we pass the session ID to the configuration of the service that is responsible for storing the images. We'll do this by using the function patchConfigurationByProduct. The first argument is the product ID by which we will later arm the calibration service. As you can guess, calibration is the identifier of the calibration workflow. This is the name of the service responsible for storing the images in the REST API. And finally, we're passing the name of the parameter that we're intending to change here. Here, that's session, exactly the same name as the variable, holding our auto-generated string. Now, after writing that change to the configuration, we need to make sure that this new configuration is also armed. And again, we do that based on the product ID and by using the function loadConfiguration. Just make sure that we're using the word calibration here for the workflow argument. This tells the API that the request is intended for those services running on the edge device that are responsible for calibration. Next, I need to insert after each motion command the function that will trigger the image and store it along with the current pose of the robot. What the current pose of the robot is obviously depends on the selected tool. Regardless of whether the camera is static or carried by the robot, we always recommend using the flange coordinate system when storing the poses. So indeed, when I look at the parameters of the motion block, I can see that the selected tool is called flange. And let me just go back to the installation tab here, and what we see is that indeed, flange is associated with a null frame. Seems to be a trait of the UR controllers not to have a predefined null frame such as on the KUKA controllers. So that next function call, which you could also look up in the UR script documentation, I'm getting the current pose of the flange relative to the world coordinate system. Again, we need to be careful with the type of the return value, which is of type pose here. Before we can pass that to the next function as an argument, we need to make sure that it's cast to the data type array or list. The remaining arguments you can leave as they're shown here, in particular the first two. I do recommend reviewing the meaning of the robot-specific arguments. That's for once the type of orientation representation used here. A vector identifies an axis angle representation. And secondly, the Boolean flag that indicates whether orientations are passed in degrees or radians. Next, I simply copy that template function call behind all the motion commands so that an image is stored from each viewpoint along with the current pose of the flange coordinate system. So let's quickly run the current state of the program, and this is what it actually looks like. In the meantime, let's log into our web frontend and navigate to the images section, and we'll find each image acquired during the calibration session, one 3D image and one RGB image, all bearing the auto-generated session number 49504. And we've arrived in the program after the 12th viewpoint. Once again, in practice, you will teach a couple of more here, so at least 20 we recommend, but 40 would be better. Anyway, we're finally in the position to run the actual calibration routine. Please consult our documentation for a detailed description of the function hand-eye calibration. I just want to run through the arguments here really quickly. Of course, we input the session that we need to associate all the images that go into the calibration dataset. And of course, we also need to pass the product ID, as the intrinsic camera data that is pretty relevant for calibration are attached to the product. And next, similar to the save image function, we need to specify in which format we expect the orientational part of the computed transformation. So again, we pass the UR-specific keyword vector. And since all orientations, respectively angles, are expressed in radians in your script, we set this last argument to false. The next argument tells the calibration whether the camera is mounted on the robot or statically within the cell. So we definitely need to set that to true here. And the last three parameters define the shape of the pattern. If you're using the calibration pattern provided by us, then typically you don't need to make any changes here. The calibration will require some time to finish, so don't worry if this function blocks for a couple of minutes. When the function returns, it will write the variable result. The variable named result is of data type array. So before we overwrite the global variable hand-eye calib that we created initially, we need to make sure to cast it into the data type pose. Let's switch to the installation tab and check the value of this variable. This is still the null frame before we run the calibration for the first time. So the only remaining question is how to validate the calibration result. And the first option is yet again to log into the front end and then switch to the trainings tab. Then what you should find is an additional card for the calibration task that we just ran. And if something went wrong during the calibration, then you will clearly see the status of the task marked as failed here. The second option, of course, is to inspect the variable hand-eye calib under the installation tab on the robot controller. Let's do a rough and quick plausibility check. What we should find here is the location of the optical center in the middle of the lens relative to the flange coordinate system. So approximately 11 centimeters in the Z direction, so that seems fine. Now the camera seems to be mainly rotated around the Z-axis of the flange coordinate system by the angle pi, or 180 degrees. So the camera is upside down relative to the flange. Then last but not least, in the case of a dynamic camera, we can select that newly created camera TCP and rotate the robot around its Z-axis. And indeed, we find that the camera rotates around its optical axis.